options that I think it's being recorded right now, so probably there's no problem with the recording. So let's get back to our slides. Let's say that we have managed to build a heap, which we can represent it as a tree like this, or in memory, remember that it will be represented as an array where the root node will be stored at index 1 of the array, and the left child of it will be stored at index 2, right child at index 3, and so on. And in general, we know that the children of a node at index I will be stored at 2i and 2i plus 1. This was one of the properties of a heap. So imagine that we have a heap like this. We have managed to build a heap like this. How do we use it? How do we use the heap structure to actually sort such an array into increasing order? Okay. The main idea was the following. Our maximum element must be stored at the root. In our output, we want this element to be the last element because we want to sort in increasing order. So what we do is swap the element at index 1 with the element at the last index so that the largest element is now at the last index. In our array, we swap these two elements. Okay. Once we do this, this part corresponds to elements in sorted order. Okay. And if we look at the rest of the figure, what we have is an almost a heap. Okay, because for every element that we check, for every element at index I that we check, the elements at 2i and 2i plus 1 are smaller than or equal to that element. This is the main heap property that we need to satisfy if we want to have a complete heap. So if we look at all these elements in here, all these 10 elements, all the elements satisfy that property other than the element at index 1. So what we do is we have seen the heapify procedure. We have seen this heapify procedure, which assumes that this index, the last parameter, stores the last index of the array where we have a heap, and only the element at index at the second parameter might be spoiling the heap property. And we have seen that heapify takes such an array A, which is an almost a heap, only this index might be spoiling the heap property, and it turns the whole array A until this last index into a heap. Okay, we have seen this in our class, in our last class. Okay, and the main idea for the heapify procedure was that assuming that I is the index that might be spoiling the heap property, and assuming everything else is fine, it must be the case that this part is a heap, this part is a heap. What we do is compare the element at index I with 2i and 2i plus 1, whichever one is larger, say element at index 2i plus 1 is larger, then we swap them, swap z and x. So now this whole thing is fine. Every node in here satisfies the heap properties, and we call our procedure heapify recursively with indicating that this index 2i plus 1 might be spoiling the heap property. Everything else is solved recursively. So we have seen this heapify procedure last week, and we have analyzed its running time, and we saw that the running time of the heapify procedure is big O log n. Or if you want to if we want to identify the running time of the heapify procedure in terms of the height of the heap, the height of the tree, the running time of the heapify procedure we say is big O of h, where h indicates the height of the tree, the height of the heap. So in terms of our heap sort algorithm, this short discussion describes the pseudocode determined with this for loop. Okay, so we swap the first element and the last element so that we place the largest element into the last index, and then we call our heapify procedure, noting that element at index 1 might be spoiling the heap property. After the initial call to these two lines of code, we will have the largest element at the last index. So this last index will have the largest element. For the rest, everything will be almost a heap, only that this first element might be spoiling the heap property, and we call heapify, and now this whole thing inside the circle is a heap. And we repeatedly apply the same idea. Now the largest element is here, and we put it as the last element in our heap, and then we call heapify for the smaller array this time, again indicating that the first element might be spoiling the heap property. Okay, so we have covered this part of our pseudocode of the heap sort algorithm last week. Since swap is a constant time operation and heapify takes at most log n time, big O log n time, and we repeat these two lines of code n times, the running time of this for loop will be at most n log n. Let's now start talking about this build heap procedure. Given an array A, let's say consisting of integer keys, and it has n elements, how do we turn this array A into a heap such that array A satisfies the heap property? Okay, for that, let's take a look at an example figure. So let's say that this is our input array A. Originally, it's not a heap because not every element in here satisfies the heap property. So for instance, if I check the element at index 4, the key value is 4. If it were to satisfy the heap property, it had to be the case that this value would have to be larger than its children, which are stored at 2 times 4, 8, and 9. So the children of index 4 are at indices 8 and 9, and we see that the value 10 is larger than 4. Okay, so for instance, this element in here doesn't satisfy the heap property. Same is true for instance, the element stored at index 1, for instance. Okay, it had to be the case that the children of this node are at indices 2 and 3. The value in here had to be larger than both of them, but we see that both values, 12 and 9, are larger than this. So this input array A doesn't satisfy the heap property. With our build heap algorithm, we need to turn this array A into a heap. Okay. Now let's first try to see which nodes, which elements in here in this input array already satisfy the heap property automatically. Does anybody have a guess? Given an array A, which elements, which nodes already satisfy the heap property? Is there an easy way to tell that? Any ideas? Can everybody still hear me? So is everybody still following the lecture? Okay, so uh, let's go one by one. So for instance, let's check index 10. Does the node stored at index 10 satisfy the heap property? It satisfies the heap property. Why? Because the children of this node, if it had any children, they would have to be stored at indices 20 and 21, but there are no such indices, which means that this node doesn't have any children. So in the tree, it is this node, it's a leaf, and it doesn't have any children. Since it doesn't have any children, it automatically satisfies the heap property. Okay? The heap property was stating that the value stored at this node has to be greater than or equal to the values stored at the children. Since it doesn't have any children, it automatically satisfies the heap property. The same is true for index 9. This is a leaf. In the tree, it is this node. It doesn't have any children, so it automatically satisfies the heap property. This one, also, this one same, this one same. So all the nodes stored at indices starting at 6, okay, but this is just, remember that this is just an example, okay. So in general, if we have an n array heap, then the first leaf will start at index n divided by 2 plus 1. This is where the first leaf starts. In here, n is 10, so 10 divided by 2, 5 plus 1, 6. 6 is the index where the first leaf node appears. So we can see that the nodes stored at n divided by 2 plus 1, next one, all the way up to n, all these nodes, they satisfy the heap property that such that the key stored at a node is greater than or equal to the keys stored at the children. Okay, any questions about this part? Every node in here, if we check for instance index 6, the node at index 6 satisfies the heap property that the key value at the node is greater than or equal to the children, because each node in here doesn't have any children. So each one satisfies that property trivially, automatically. Now, the first element, the first node that might spoil, that might not have the heap property is the element at index n divided by 2. This is the first non-leaf node. So in our tree, it is this one. This is the first node that is not a leaf. In general, the element at index n divided by 2 might be the first index that may not satisfy the heap property. Now, what will we do with a node that might not satisfy the heap property? What we can do is remember that we now have a heapify procedure, which basically takes an index I and makes sure that everything, all the indices after 5 satisfy the heap property. Okay, so what we are going to do is call heapify on this index. Okay, because everything below, everything in here satisfy the heap property. Only the index at 5 might be spoiling the heap property. And remember that this was exactly the figure that we had for our heapify procedure. Everything in here satisfies the heap property, all the indices, the nodes at all the indices following index I satisfy the heap property. Only the node at index I might be spoiling the heap property. And our heapify algorithm, this heapify algorithm, fixes the whole thing, turns the whole thing into a heap starting at index I. This is exactly what we need in here. We know that elements at indices 6, 7, 8, 9, 10, each one satisfies the heap property. At this point, element at index 5 may not satisfy the heap property. So what we are going to do is call our heapify algorithm, heapify algorithm. What are we going to pass as parameters? Our array A, and then we will say that 5 is the index that might spoil the heap property, and then as the third parameter we will indicate the last index of our heap, which is 10. Now after this heapify call, A, 5 and 10, after this finishes, we know that now everything to the right of this line, everything starting at index 5 satisfies the heap property. Okay. Now imagine that you should be able to imagine that we can now repeatedly do the same thing. We can now call heapify with index 4. If we call heapify with index 4, since everything after 4 satisfies the heap property, and we call heapify on this index, after that procedure call, everything to the right of the index 4 will satisfy the heap property. And we can do the same thing with index 3, call heapify on index 3, and everything to the right of the index 3 will now satisfy the heap property. Call heapify on index 2, and finally call heapify on index 1. So for this specific input example, if I call heapify with index 5, followed by a heapify call on index 4, a heapify call on index 3, a heapify call on index 2, a heapify call on index 1, at the end of these 5 heapify calls, you should be able to see that this whole array should turn into a complete heap. Is this clear? Is this discussion clear? Any questions about this part? Does anybody want me to repeat any part of what we have discussed in terms of the build heap algorithm? We have just shown how the algorithm should work on a specific example. We will now go on to see the pseudocode of the algorithm so that it will be more clear. But is everything that we have discussed on the example array clear? Can everybody still hear me? Okay, let's now see what we have discussed on this example, let's now see the pseudocode of the algorithm. So remember that, let's redraw our array. This is index 1, this is index n, and this is the middle part. Remember that n divided by 2 is the first index that is not a leaf. Everything in here is a leaf. So we first call our heapify with index n divided by 2. Okay. Next, once this is finished, we call it on index n divided by 2 minus 1. Next, we call it on index n divided by 2 minus 2, and so on all the way up to index 1. If we make these n divided by 2 heapify calls, at the end, everything will turn into a heap. The whole array A, in the sense that every node will satisfy the heap properties. So within a loop, we repeatedly call heapify with the necessary indices. Is the pseudocode clear? It's just basically the steps that we have discussed on the example. It's turned into pseudocode. Within a for loop, call heapify with decrementing indices starting with the first non-leaf index and going all the way down to 1. Is the main idea of build heap algorithm clear? If it is clear, let's try to now analyze its running time. Any ideas regarding the running time of the build heap algorithm working on n elements? So what could be the running time of the pseudocode of this for loop? Any ideas regarding the running time of the build heap algorithm? Anyone? So let's just try to pick somebody in random. So for instance, let's ask Turgay. Turgay, can you hear me? Okay, can you make a guess regarding the running time of this pseudocode for build heap? So we have a for loop that starts at index n divided by 2, goes all the way down to 1, and each time it makes a heapify call. What is the running time of this for loop? What is the running time of the build heap algorithm? Can you make a guess, Turgay? Okay. Do you remember we discussed the running time of the heapify algorithm? We discussed this last week, and we just repeated a summary of the topics we have covered, which included heapify, at the beginning of this class as well. We have just actually mentioned the running time of heapify. Do you remember the running time of the heapify algorithm? Does anybody remember what was the running time of heapify? Log n. So if we have n elements, then the heapify at most will require log n time. So the running time of heapify is big O log n. If that is what is the running time of this whole for loop? What is the running time of the build heap algorithm? Anyone? So heapify requires big O log n time. Then what is the running time of the for loop? How is it? So for loop iterates n divided by 2 times. That is true. What is the whole running time of the for loop? Within the for loop, we make a call each time at each iteration of the for loop. We make a call to heapify. Yes, so it is n log n because heapify is big O log n, and we call heapify n divided by 2 times. Since we can forget about the constants in our running time analysis in terms of big O notation, we can forget about that 1 divided by 2 part. So the running time will be n times log n at the most. So see that actually this analysis, this running time analysis is a bit generous. So actually if we do a more careful analysis of this build heap algorithm, we will see that it is not even n log n. It's even something smaller than n log n. Can anybody see what could be the reason for that? Notice the following. This is the first call that we make for index n divided by 2. How much running time will the heapify cost us when we call heapify on this first index n divided by 2? Is it log n running time? Do we spend log n running time when we call heapify on index n divided by 2? Does anybody have an answer? Have a guess? So right now I'm not asking about the running time of a heapify call in general. I'm asking about a specific heapify call. So if I call heapify on A, this index I being equal to n divided by 2, and this third parameter is n. What is the running time of that specific heapify call? Any guesses regarding that? If I look at, for instance, let's see our specific example. So if I call heapify on index 5, does that heapify call require log n time? Or for a more general array figure, if I call heapify on index n divided by 2, how much running time does that specific heapify call cost? Can anybody turn on their microphone and shortly describe how a heapify, or what steps are exactly executed by a heapify call on index n divided by 2? What comparisons are executed, what swaps are needed, and so on. So I don't see any answer. Why is there no answer? Are you guys not following the lectures, or is there any part that is not clear regarding the heapify procedure, for instance? Okay, let me reiterate. So if I call heapify on this index and divided by 2, remember how heapify worked. This is the element that might spoil the heap property. It's left subtree, it's right subtree. What we do is compare this node's key with its children and swap with the larger child and recursively call heapify on whichever child we have done the swap. Let's say the right child is larger, we do the swap, and now we call heapify on this index, and so on. So recursively, this is what happens. Let's see that. Let's see what happens with the specific heapify call on this index n divided by 2. We will be comparing this element at index n divided by 2 with its children, but it only has one child, which is at n. So we will compare these two. If the element at index n is larger, we will do a swap. Swap the element with index n divided by 2 and index n. Swap them. And then call heapify on the next index, which is this one. Now heapify on this index won't do anything because this index doesn't have any children. It's already a leaf. So our heapify call on this index n divided by 2 didn't actually require log n operations. Okay, it just required one swap, possibly one swap, and that's it. The same might be true for the next index n divided by 2 minus 1. All we will do is maybe a single swap, and then that's it, we will stop. So for the elements around here, note that we won't spend log n time. For the initial elements, we will be spending log n time. So only when we call, for instance, heapify a on index 1, maybe we will spend log n time. On index 2, maybe we will spend log n time. But for much of this array part, here our heapify calls will not cost us log n time. So if we do a better analysis, we can take this into account that for most of the elements in here, our heapify does not cost us log n time. How to do an exact analysis of this? We can do our exact analysis of what the running time of the whole build heap algorithm will be by looking at an analysis based on the height of the tree. Remember that for heapify, we have given two types of running time. One of them was that heapify will cost us at most log n time, where n denotes the number of elements we have in our array. The other analysis was in terms of the other running time that we have given was in terms of the height of the tree. Each heapify call requires big O h running time, where h is the height of the tree. Okay, so let's do an analysis of that sort. If I look at this tree, for instance, remember that this part are just the leaves. So we don't do anything related to this part. Okay. Now these are all leaves. We have n divided by too many leaves, where for our build heap we just spend constant time, because all we do is that we check that it doesn't have any children. So for n divided by 2 elements, let's say that we spend one time. And How many parents of these leaf nodes do we have? Half of this. So we have n divided by 2 square many nodes that are the parents of the leaf nodes. So for instance, this node at index 3, 4, and 5. There are n divided by 2 square many of them. For each one of those, remember that we call our heapify algorithm. And for each of those, our heapify, let's say that requires 2 primitive operations. Okay, because all we will do is, for instance, for index 5, compare it with its children, maybe do one swap and call heapify on index 10, which will not do any further swaps. If we go one level up, we will have n divided by 2 cube many elements, many nodes, and we can assume that for each of those nodes, our heapify will do almost 3 primitive operations. Okay, so for the next, it will be n divided by 2 to the 4 many nodes, and for each one, we will be spending 4 primitive operations for our heapify. So this part denotes us the height of the index that might be spoiling the heap property. All the way up to n divided by 2 to the log n many nodes at the highest level, and for each of those nodes we will spend log n time. This is the height of the root node, for instance. So if we sum up all these values, that should give us a better running time analysis for our build heap algorithm. If we look at that sum now, it is this one. So we have n divided by 2 to the 8, almost many nodes at height h, and for each one we will spend big O H running time for the heapify call. Okay, and we have log n many levels in our tree. If you look at this time sum, we can take n out and we have a summation of this form which evaluates to a constant. So at the end we see that the running time, or the value of this sum, is n times 2, which is big O n. So the running time, if we do a simple analysis, we can see that the running time of build heap is big O n log n. Okay, but if we do a more careful analysis, we see that it's actually less than big O n log n. It is at most n, big O n. Okay, but note that this analysis in here does not change our running time analysis of the heap sort algorithm. Let's get back to the main build heap sort algorithm now. Okay, this was the pseudocode of our heap sort algorithm. Now we know that build heap requires big O n time. For the rest, the for loop in here requires, so this one big O n, and the for loop requires big O n log n. So overall, the running time of our heap sort algorithm will be big O n log n, because it is n log n plus n. So since n log n is a larger function, then we can forget about the n part, and the running time of the heap sort algorithm will be big O n log n. Do you have any questions regarding this discussion, regarding the running time analysis of the heap sort algorithm and the build heap algorithm that we have seen in this class? Any questions? Can everybody still hear me? Okay, let's try to see how the heap sort algorithm works on a specific example. Let's say this is our example, or in the array format, in the array representation, this is our input array A, and now we want to sort this array A into increasing order using the heap sort algorithm. The first thing that the heap sort algorithm does is calling build heap on this array, so that build heap will turn this array A into a heap. Let's see how the build heap algorithm works on this input array A. Remember, as we said, the indices n divided by 2 plus 1 and on, in this example, indices 6, 7, 8, 9, 10, they are all leaves. Okay, so we don't have to do anything about them because each one satisfies the heap property. The first index that might spoil the heap property, going from right to left, is index n divided by 2. In this example, index 5. So our first call to heapify is on index 5. Okay, what does the heapify algorithm do when it is called on index 5? It will compare the element at index 5 with its children, which are at indices 10 and 11. Well, 11 doesn't exist, so it will compare it against the element at index 10, and it will do a swap if necessary. In this case, the element at index 5 is 15, the element at index 10 is 5, so element at index 5 is already larger, so no swaps are necessary, and this heapify call will have finished its job. Okay, now at this point we know that if we look at our tree, elements in here now, each node in here starting at index 5 satisfies the heap property. Next, we call our heapify on the next index. So we call our heapify now at index 4. What does that heapify call do? It will compare this one, the element at index 4, with its children, which are at indices 8 and 9. So the element at index 8 is larger, then it will do a swap. It will swap 10 and 4. So now 10 will be here, 4 will be here, and it will recursively make a call to this index, but that recursive call won't do anything because this is already a leaf. It doesn't have any children. So now we have this part of our tree all turned into a heap. We have 10 in here and 4 in here. Next, we call our heapify with the next index, which is 3. Okay. The children of the index 3 are at 6 and 7. We will compare them and we see that the largest one is already at index 3, so no swaps and no further recursive calls are necessary. That part of the heap remains as it is. Our next heapify call is on index 2. Okay. Let's see index 2. We will be comparing index 2 with its children, which are at 4 and 5. The largest one is 15 at index 5. So it will swap 15 and 12. So 15 and 12 are swapped. Okay. And next, another recursive call is made on index 5. Another recursive call to heapify is made on index 5. Now that call will compare index 5 against index 10. 11 doesn't exist, but we see that 12 is already larger than the element at index 10, so no further swaps are necessary. And this corresponds to the part of the heap that we have now modified. Our final call to heapify is on index 1. We do the same thing. First, compare index 1 with its children, indices 2 and 3. Note that we now have actually 15 in here. So the largest one among these three is 15, so we swap 7 and 15. So this becomes 7, this becomes 15, and we recursively call heapify on the modified part. So next we will be comparing 7 versus the element stored in here and so on. So this is the heap after we call heapify on index 1. Okay. Now, everything in here satisfies the heap property. Remember, for the rest of our heap sort algorithm, what we will do is swap the first index with the last index, because the first index contains the largest element. So swap these two, turn the rest of the array into a heap, indicating that the element at index 1 might be spoiling the heap property. So if we look at that figure in here, we have swapped 15 and 5. Now this part is sorted. For the rest is almost a heap, only that the element at index 1 might be spoiling the heap property. So we make a call to heapify on index 1. What will that do? It will compare 1 versus its children, which are at 2 and 3, and the child at 2 is larger, so it will swap them. So 5 will be here, 12 will be here, and then it will call heapify at index 2 recursively. This one compares 5 with 10 and 7. 10 is larger, so it will swap them. 5 will now be here, 10 will be here, and we will make another recursive call to heapify on this index. So now that will compare 5 versus 4 and 2. 5 is already largest, so it will stop the heapify procedure there. And we will have this array. Okay, 12 is at index 1, 10 is at index 2. This part is the same as before. At index 4 we have now 5. The rest is the same. So in our figure now what we have is that this part is in sorted order, and for the rest we now have a heap, and we can repeat the same procedure. Basically swap the element at the root with the last element. So we will swap 12 and 2. 12 will now be in a sorted order. This part will be sorted. The only element that might spoil the heap property for the rest will be this one, and we call heapify on index 2. That one will now turn this whole thing into a heap, just like in this one, and we repeat the same procedure. Swap the first element with the last one, 10 and 4, and now we have 10 in its sorted order. The rest is almost a heap, with this one might be spoiling the heap property, and we call heapify on index 1, and so on. So at home, as an exercise, try the rest of the steps of the heap sort algorithm to complete the steps of the heap sort algorithm on this given inputs. Any questions about this discussion? Does anybody have any questions regarding the heap sort algorithm? Okay then, let's stop here for today, and tomorrow we will start talking about another type of a sorting algorithm, which will be called quick sort, and I will see you all tomorrow then.